Hi, everyone. Welcome to today's webinar, Machine Learning and Robotics in Healthcare Devices and Rehabilitation. At ODSC, we're excited to collaborate with the best and the brightest in the industry to present to you at our events, conferences, and webinars. And we are happy to have Alishba Imran, a machine learning developer at Hanson Robotics Limited today. For those who new to ODSC, we are one of the world's largest applied data science and AI communities. We have around 65 local chapters across the globe, as well as with in-person and virtual conferences in Boston, Dublin, San Francisco, New York City, Sao Paulo, Bangalore, Singapore. You can visit odsc.com for more information on our speakers, trainings, workshops, and career tools. In addition to that, you can see there what is our plan for 2021, and especially for the first half of the year. And today I would like to emphasize on the two huge events that we have planned for June and November. It's called Virtual ODSC Europe 2021 and ODSC West 2021, which will be in-person conference in San Francisco. So I hope you will have a chance to visit us there and to join us actually for a first in-person conference after this almost 2 years break. And on these slides, you can find list of the upcoming events with the QR codes to their pages and registration links. Feel free to choose the one which you are interested in the most. And there is a lot of as well free events and paid one, a lot of different options. So you definitely can find the one that will work for you. And I would like to emphasize that in June, on 8th to 10th, during Virtual ODSC Europe, we have General Pass, which is free of charge. And it includes ODSC keynotes, ODSC Europe virtual extra events, which we have around 2 each day, and AI Expo, demo talks, Career Lab, Expo, ODSC Europe, some selected talks that you will have access to, and everything is for free. So if you're interested in the content and the speakers lineup and in that specific pass, I will share with you the link here so you can register, or you can find it as well on the on our website. And if you're interested in trainings and workshops, webinar attendees can get an additional 10% off on your tickets by using Meetup 2021 discount code at the checkout. As just general free pass doesn't include the workshops and trainings. So if you're interested in that, in total, there will be, with this discount code, there will be 40% off, but only this week, as we have a ticket sales ending week. So feel free to catch the best price for this specific conference. And additionally, there's a lot of questions regarding the certifications and whether we have any at ODSC. We have a live trainings for the certification of completion at the end, and as well we have a lot of certifications and tests and assessments going on the AI+ training platform. And we are adding new contents each week. So you may go there and find more courses and certifications on machine learning, deep learning, NLP, and many more. That's actually the platform where you register for this webinar, and that's the platform where you can find the recording of this webinar after the session ends. So it will be around 1 or 2 days. The recordings will be available, so you can stay tuned to it. But yeah, everything on that platform, so we hope you'll have a chance to check this out. And just a quick point before we start, feel free to ask your questions in the question tab on your right hand if you're sitting from the laptop, but if you're watching this webinar from your phone, the question tab will be on the bottom of your screen. So don't worry, every questions are coming up to us. We are looking to it. We'll be answering it, and Alishba will take care about that after the webinar during Q&A session. If there will be any organizational questions, I will help you with that. And as I mentioned, recording will be sent out to you with the slides. Alishba will share a lot of useful links for you after the session. So I hope you will stay tuned to attendee follow-up email tomorrow. And yeah, without any further ado, thank you a lot for joining us today. And I hope you enjoyed the session. And we are ready to begin the presentation. Alishba, the floor is yours.
Thank you. Thank you for that introduction. So yeah, feel free to, again, put your questions in the question tab. I'm going to be answering them towards the end, so there will be a couple of minutes for Q&A, and I'm happy to also share any links throughout the presentation that you might want to look into, as well as the slides. $20,000. This was the number that would define the future for Sarah to be able to walk again. A few months ago, I visited a rehabilitation center to meet my grandparents, where I had the chance to meet with Sarah. Sarah had recently lost part of her leg in a car crash and needed access to a prosthetic. The process of getting one was very long, hectic, and cost her over $20,000. To this day, Sarah feels uncomfortable walking with her prosthetic and has difficulty moving around to complete everyday tasks. This isn't just a problem that Sarah faces, it's a global problem. Prosthetics today can cost anywhere from $10,000 to $100,000 for more advanced myoelectric controlled prosthetics. It can also take anywhere from 3 months to sometimes even a year to get used to training and using the arm during rehabilitation and clinical sessions. Even after you get access to the arm, you usually have to manually manipulate it on a day-to-day basis to pick up or interact with different objects. And the WHO has estimated that over 150 million people globally don't have access to prosthetic devices for these reasons. Now, technologies like artificial intelligence are really, really exciting and promising because they're allowing us to discover and build cheaper and more automated, efficient alternatives to machines and devices like prosthetics that interface with humans. This work is being developed at the intersection of AI, rehabilitation tech, humanoids, and medical devices. Now, to get a better understanding of kind of what this research is, and I'm going to be breaking down some of the key areas that I've been working in and that I find really exciting in the future, we first really need to understand the key areas within a subset of AI, which is machine learning. And so the main areas within machine learning are supervised learning, unsupervised learning, and reinforcement learning. Within supervised learning, you're essentially looking at a classification of images. So you can think of any sort of image classification, or let's say you have a data set of like X-rays or MRI images, and you're trying to do some sort of diagnosis based on that. We also have regression models within supervised learning, where you're looking at dimensionally reduction, which is essentially big data visualizations or any sort of image recognition task. This also includes things like clustering, which are commonly used for targeted marketing, as well as recommendation systems. Reinforcement learning itself is used within a lot of different tasks, but it's mainly used to make real-time decisions, commonly within robotics for tasks such as navigation, manipulation, as well as gaming. Supervised learning is a concept that focuses on labeling of the actual training data. And so the model first learns by giving it some sort of data that it can train itself on. The training data contains different patterns, which the model eventually learns. And then it also contains the inputs that correspond to the outputs and the hidden patterns within them. The algorithm will essentially learn these patterns and then try to apply this knowledge to unseen data with the aim of being able to predict some sort of future values using past data. And so mathematically, supervised learning algorithms can be defined as different functions, but often if you have a very simple type of prediction, they can be showcased as just a very simple linear function. So unlike supervised learning, in the case of unsupervised learning, we actually do not have labeling of data or any sort of training of the model that happens. Essentially, the model learns through training itself from the data that you're feeding it in for making that prediction, and is able to discover hidden patterns within it, again, with the goal of being able to make some sort of future prediction based on past data. Reinforcement learning itself is very similar to the way that humans learn. If you think about the process that we go through from all the way from being a child to being an adult, we're learning through the process of trial and error. So you can imagine that you have a robot, which in this case is your agent, the thing or the object that's actually doing the learning and making the decisions. And so in this case, you're trying to train this robot to learn to walk just like humans would. And so your goal here is to be able to get that robot to walk successfully. Now the robot will go through a process of trying to walk, maybe failing a few times and then trying again until eventually it learns how to walk. And it learns the correct way to walk through reinforcements that are given to the actual agent from the environment. And so it gets a positive reinforcement or reward every single time that it walks correctly. And it gets a negative reinforcement every single time that it walks incorrectly. Now, there's many ways in which machines can be applied to enhance human-machine interfaces, and human-machine interfaces, or HMI, are essentially just any sort of machines that you can think of where there is some sort of interaction between humans that's happening. And often, we see this within robotics where there is still some sort of aspect of humans being involved in the operations of these robots, or humans even, doing a task and getting those robots to replicate that task. And so one of the ways in which we see AI being applied to HMI, or human-machine interfaces, is through sensing and perception tasks. And so in this case, sensors are used to sense the environment, and then machine learning techniques can be applied to actually process this data by essentially computing the difference between the present state that the machine or the robot is in, and then the goal state that you would eventually like it to be in. Using this, actuator commands that do the task or execute on the task are created to then move that machine or robot, and these are sent to the actuators, which eventually act on the environment. Another example that is commonly used here is for manipulation tasks for a machine or a robot. And so here some sort of sensory input is taken. This can often be just in the form of images. This is sent through a neural network for which a manipulation prediction is made. So for example, let's say you're trying to figure out, based on a lot of different objects that are in your environment, what would be the best grasping pose to actually grab that object. So for example, if you have a cup, how do you grab that cup, and what position or what type of formation does your specific gripper need to do, whether that be like a hand or just a parallel gripper that's shown in this image here to actually grab that cup. And so through doing that, you're training the model on a bunch of grasping poses that it's learning. And so when you showcase it to this new object, it now tries to generalize to that and predict what would be the best type of grasping pose. And so the control then is executed through some sort of velocity command. So as an example, let's say you have an RGBD sensor that is used to capture images of the objects within this workspace. And now the algorithm for manipulation that is being trained on a broad range of different objects is now tested on a new set of objects that have never been seen before by the robot to get it to try and generalize. Using ML, we can also bring in the human in the loop, and having human feedback is really important for a lot of different tasks, but a common example that is seen is within reinforcement learning. So let's say you have an agent that explores and interacts with its environment. Periodically, clips of the agent's behaviors are then sent to a human operator who is then asked to select which one of the tasks that the robot is doing best actually showcases the steps towards fulfilling the desired goal that you've set for that robot. And so in this case, the human's choice is used to further train a reward predictor, which in turn then trains that agent. And so over time, the agent is learning to maximize for the reward from the predictor and improve its behavior in line based on what the human's preferences are. So for me, Sarah was a huge part of my journey, and just getting more involved in robotics and AI and learning about applications within rehabilitation. And after speaking to Sarah, I got inspired to start this project called Vision Arm. So I worked with a professor and a master's student at San Jose State University to develop a new convolutional neural network that uses techniques like computer vision and reinforcement learning to fully automate the process of identifying, grasping, and interacting with objects for the prosthetic arm. And so we also developed a material which was 3D printed and a new design that was able to reduce the cost of these prosthetics from about $10,000 on average to just $700 by making the hardware and the software a lot more accessible and obviously more affordable to people globally. I also received mentorship from developers at Myont who develop essentially myoelectric bands. So they're looking at, using muscle signals to help with the prosthetics. And that was really important because we wanted to understand for an amputee, what is their intent or what type of task are they really trying to do? And so through interacting and using and analyzing some of those myoelectric signals, we were able to better understand that. And I also worked with researchers at the Blink Lab who supported me on developing some of the actual mechanical side of the project. So we're currently publishing some of our research in IMECE as well as IROS this year. Now, a little bit more about how this works. So current prosthetics are controlled directly via the user's myoelectric signals, which essentially is just electrical activity of the muscles that are recorded from the skin surface of where the stump is placed. And so a myoelectric band can be used to actually capture those signals and understand the user's intention. And so this, alongside a camera that's placed on the actual prosthetic, is used to capture an image of the objects within the environment and then process these by extracting key features such as what objects are in view. And then these images are sent through what we used, which is called a generative grasping convolutional neural network, to make a prediction for the best grasp to grab that object. And so the identified grasp and the myoelectric signals are sent to the prosthetic controller then for proportional control. So the GGCNN, or the grasping convolutional neural network that actually did the prediction for the grasping pose, is essentially a real-time generative grasping pipeline. And the way it works is through a camera that is mounted onto the wrist of the prosthetic, and that camera captures depth images that contain an object that we are trying to grab. And so the GGCNN generates antipodal grasps, which are basically parameterized as the grasp quality of the grasp that it's identified, the angle at which you need to grab that object, the grip, and the gripper width that it needs to be at to grab that. And so that's done for every single pixel in the input image within a fraction of a second. So one of the reasons we chose to use this algorithm was because it's a lot less kind of computationally heavy than some of the other algorithms that exist for grasping. And so it's a lot easier for us to get real-time feedback and real-time execution of the actual grasp. And so from this, the best grasp is then calculated and a velocity command is then sent to the robot to execute on that. So the closed loop system that we use is also capable of grasping dynamic objects and reacting to control errors. So this works by grouping objects by the size, shape, and orientation that they have. So similar types of objects are grouped together so that it's easier to identify the type of grasp that would be needed to grab them. And so specifically, we programmed the hand to perform 4 different grasps. We looked at palm wrist neutral, which is when, let's say you're just picking up like a cup. Palm wrist pronated, which is when you're picking up, let's say, like a TV remote. Tripod, which is any grasp that involves your thumb and 2 fingers, and then pinch, which is just your thumb and your first finger. So this work does not just apply to prosthetics, but it can also be applied to a wider range of rehabilitation devices, one of which that I've been looking at is hand exoskeletons. And these devices are often used for recovering motor function of the hand for stroke patients. And we can use soft robotics and machine learning for the development of these low-cost and easier to use, more portable rehabilitation gloves for stroke patients. So these often contain a glove, as you can see on this image, and the fingers themselves are covered by these soft actuators, and the sensing and control of those actuators are run by an ML algorithm for individual control and sensing of each finger. And so the entire glove itself in this scenario is pneumatically controlled. So diving deeper into this problem a little bit, when somebody has a stroke, there's often a golden period within optimal recovery for the actual hand function, which occurs typically within the first 3 months after a stroke occurs. And so the goal is we want to be able to improve hand motor functions within this period through doing identical and repetitive movements by the impaired hands. And this is just because your brain recognizes that because of neuroplasticity after the stroke occurs within that period. And so this is a huge problem because 15 million people suffer from a stroke worldwide. It's the second leading cause of death globally. And of those 15 million people, 5 million people end up dying, and another 5 million people are permanently disabled. And so really this tells us that there is a huge problem here, and we need better treatments for stroke patients, especially when it comes to the recovery stage after rehabilitation and after they've been released from the actual hospital. And so traditional hand exoskeleton devices that are used for doing that are very limited today because of their high cost. They're also very rigid, they weigh a lot, and there's a lot of constraints on the actual joints because there's non-actuated degrees of freedom, which end up posing complications on the actual tasks or the movements that a person can actually do with them. And these problems mainly stem from their actual components because they're linear actuators and also have very rigid linkages. And often a lot of these, as you can see in these images, are actually held within clinics and rehabilitation centers. So these devices are very much not portable. You can't easily take them home. And they weigh a lot, they're very bulky, and you often even need a professional there in the room to help you with the operation of the system themselves. And this is where soft robotics comes in, because soft robotics have a huge advantage to solve this problem due to their higher flexibility. They also have a lot more safe operations compared to traditional mechanical robotics. They're also a lot more lightweight, and they have simplified production. So overall, that results in also having lower manufacturing costs. And further, there's a lot of work being done to actually use 3D printed materials to create the actuators themselves, which can further reduce the costs of manufacturing and production. And soft robotics themselves are often capable of generating forces and torques to support the bidirectional finger movement, which consists of finger flexion and extension, which is needed and really important for the tasks that are done. And the soft robotic glove itself also passively controls each finger through the elasticity of the actuators that happen on fluid decompression that comes from the pneumatic systems that are controlling them. But because soft robotics are so flexible, they're actually very limited by their output force, because when you think about having an exoskeleton device that's controlled by soft robotics, you need to be able to supply a strong amount of force when actually grabbing the different objects and interacting with them. And so the development of control algorithms still remains a very huge challenge for soft robotics because of the nonlinearity of these soft actuators and their interactions with the environment. So existing methods that are used often for controlling these soft actuators can be categorized into three main types. So there's model-free controllers, which are usually based on some sort of machine learning technique or some sort of empirical method. These controllers have good advantages because they they have higher non-linearity, they are non-uniform, and they also work well within unstructured environment situations where actually being able to create a physical model is really, really difficult. And then you have model-based controllers. And with these, you often need some sort of analytical models to actually derive the controller. And these controllers have more accurate and reliable performance than model-free controllers because they have more uniform soft manipulators that can be used within environments that are already well known. But the caveat is, they usually require very well-defined dynamical models for the actual soft robotics, which is difficult to construct based on a lot of rigid body assumptions that come with soft robotics. And then you have kind of an interesting intersection of both with hybrid controllers. So you're combining both model-free and model-based controllers, and these are usually based on, so you have analytical models that are coming in that are used to help with capturing like the main parts of the system's intrinsic properties. And then you have a more data learning or machine learning approach to compensate for any sort of dynamical uncertainties that might exist. So the way that you can control these soft robotics is through the usage of reinforcement learning. Basically by making these machines that are able to execute and identify optimal behavior in terms of either a certain reward or loss function that you're defining. And so within a typical reinforcement learning problem, there is usually a learner and a decision maker called the agent. And the surrounding with which it interacts with this is called its environment. And so the environment in turn provides some sort of reward and a new state based on the actions of the agent itself. So within reinforcement learning, you don't have to explicitly teach an agent or tell it what to do or how it should do something, but rather you present it with some sort of rewards, whether that's like positive or negative rewards based on the actions that they do. And those are used to actually help the soft robotic learn. And so this can be done through something called the Markov decision process, or MDP. And so the aim of MDP is to train an agent to find a policy that will return the maximum amount of rewards for taking a series of actions within a few states. So in our specific scenario where we're trying to control a soft robotic for this exoskeleton hand, a set of predetermined points to represent the state of the soft robotic can be used as the actual set of the states. Now, the state representation of the entire soft robotic would just be the combination of the states of each section of that soft robot. And so a section state would be represented by 3 coordinates, which is the beginning of that soft robot, the center of it, and the end of that soft robot. The action itself is defined as just a movement of one of the motion sections within that soft robot, and in that section moving within discrete directions. And the reward function can be defined as just a linear correlation function of the states. So I use a function approximation of Q-learning to train the actual control policy. And so each episode, the soft robot executes a sequence of actions from the initial state. And then on the basis of the state, action, and reward representation that I just defined, a final action is introduced. And so this action itself does not affect the actual shape of the robot, but it's rather just indicating when the episode will be stopped. And so the entire learning process just consists of repeating episodes from the initial state all the way to the final action. But because of the continuous space and nonlinear setting of the problem, you can also map the actual state space into a more high dimensional linear space. And so this data structure can be seen as using just a neural network with just one hidden layer. And that just makes it really easy to execute. And then the data structure that is a neural network with the one hidden layer is then fed into this Q function, which contains the state and the action. And so the Q function itself is just the mean value function associated with all of the step numbers. And so I actually simulated the control of a soft robot gripper using a function approximation Q-learning to train the control policy for a very simple, just grab and pick and place simple manipulation task. And so I did this using the Sophia framework and using the Soft Robotics Toolkit, which was published and open sourced by the Harvard Biodesign Lab. So I'm just going to quickly show you guys a clip of kind of what this looks like. All right. So yeah, that was a quick kind of demo of what that looks like. And so in this case, I was executing on that manipulation task, but the simulator itself can also be just used to sample in the state space before any sort of reinforcement learning is applied. So you can imagine just randomly executing actions and then computing the Q value within each of the sample. And so by sampling the state space, you can also use just a gradient descent algorithm to compute the weight of this network. And then use the Q function that was trained to then set this, this as the initial Q within the simulation step to actually help improve the performance of the simulation. So in terms of actual execution, for closed loop control, from each time that you obtain the current state of the soft robot from the actual sensor, and then you just use the actual current state of the soft robot and use that as an input into the queue function to then get and execute the optimal action for the policy. So a soft robot itself is likely interacting with kind of a wide variety of objects within its environment, but some of this information of this object and the robot itself can actually be difficult to perceive or interpret. For example, just simple things like the hardness or the weight of an object that the robot is trying to pick up can potentially interfere with the actual interaction that it's trying to do. And so here's where, there's other areas we can apply ML where there's a lot of value add. And one of these applications that I wanted to highlight was for sensor characterization. And so sensor characterization just involves the collection of raw sensor data that is then aligned with ground truth values within a controlled and monitored environment. So you can think about like a lab setting, for example. And so this data is then typically provided as an input to a neural network to predict future values such as the force, pressure, strain, and location of the object that you're trying to grab. So in contrast, there's also systems characterization, which collects sensor data in a less controlled environment that mimics their use in field. And so in this case, ground truth measurements such as force are more difficult to obtain because you're in fields, things are obviously less controlled and less known. And so often the way that you can kind of circumvent this is by mapping out just higher level classification. So just looking at, what is the grasp success, or looking at recognizing the texture of the object. Another application is actually learning the controllers. And so learning controller functions by essentially iteratively evaluating the performance of the resultant trajectory for a controller that you want with respect to some sort of cost function. And then you're essentially updating the parameters over time to increase the performance through optimization. So I briefly mentioned, but the Harvard Biodesign Lab is a great group of people that are working on kind of cutting edge research in the space to develop a soft robotic glove that provides repetitive stretching, exercise, and grasping assistance to help people with limited hand function due to any sort of neurological condition. So in this case, they're actually using soft robotics and applying that directly to this problem, and also commercializing that through studies that they're doing, and hopefully get, eventually publishing this glove for everyone to have access to. So I just wanted to mention that as kind of a real life example of how some of this work is being applied. Within the upcoming months, I'm also going to be working with Kindred AI on developing imitation learning techniques for more complex manipulation tasks. And so imitation learning, it's kind of within the name itself, but it's essentially when you have robots that are programmed to learn by imitating a task or something that a human is doing. And so typically you need to actually train the robot on a huge amount of, or a series of human demonstrations before they can actually effectively reproduce the desired behavior that you would like. One technique that is used to do this is actually through domain adaptive meta learning. And this is when many demonstrations of many different tasks that are performed by both teleoperated robots and humans are collected. And then the human demonstration is provided for computing the policy update and evaluating the updated policy using the actual robot demonstration that was performing the same task that the human was doing. And so teleoperated robots have a lot of applications within just the medical industry. You can think about, using medical robot systems for allowing procedures such as surgeries, treatments, diagnosing them, and being able to conduct this, surgery from short or even long distances, also while utilizing any form of wired or wireless communication network. So a lot of work is being done to use VR headsets that humans are, wearing, and haptic feedback where they're doing the action, and that's being controlled by the robot that's replicating that task. But there's also work to just, reduce the hardware and make it more less bulky and less more accessible through just using your cell phone and just an application on your cell phone itself to control the robots. And so a lot of work here is also being done within robotic manipulation, just telecommunications, and developing vision systems that can be used to further enhance the actual precision during the robot surgery that's doing surgery, and just overall research in this area. So alongside my other work, for the past few months, I've been working on trying to tackle some of these problems by also developing more generalization techniques with a company called Hanson Robotics. So Hanson Robotics is the company behind Sophia the robot, and you might have seen or heard of Sophia. She's the life-sized human-like machine. She's able to make multiple facial expressions, understand sentences, and actually hold and have casual conversations with humans. And I'm helping to develop an algorithm and working on the research and engineering side to help improve the sensing, perception, and grasping of the arm. And we're hoping to be able to use Sophia for applications within autism treatment, medical depression treatment, medical education, and insurance education. We have recently done a study with her where we had her speak to people during meditation or just in general hold conversations with people, and we tried to measure how humans actually interacted with her and how they felt during that interaction. And so our goal is to be able to deploy her as a tool to help conduct some of these research studies and better understand human and machine interactions as well. And so we presented some of our research on this work at NeurIPS last year, as well as AAS this year. Now, the reality is that we don't have artificial general intelligence or this idea of AGI that we're constantly hearing about. And AGI in itself is it's difficult to define, and there's a lot of debate in the industry in researchers and just how they actually define it. But I would say that loosely you can kind of describe this field as the ability for a robot or machine to understand or learn any sort of intellectual task that a human being would be able to learn. And so robots like Sophia or other humanoids that are developed today are made up of hardware and software. But when we compare a lot of the hardware that they have to humans, we'll see that they're still not at the abilities of humans. Right, our human brain is able to process so much information with the millions of neurons in our brains that are powering at a millisecond and compute and process that information within just a split second. But when we think about a lot of the hardware we have, we're still very much limited by the amount of storage they have or the memory they have and their ability to actually compute things really fast. And this is why there's so much development recently on actually developing, GPUs, CPUs, and TPUs, because we need a lot of those computation, like we need more computation hardware for helping us build more ML models that can run and do a lot of these complex processes that we need them to do. So there are obviously a lot of researchers that are focusing on these areas to develop different aspects of AGIs. The first area that I want to highlight is within sensory perception. So if you think about algorithms like computer vision, which is just the ability for these machines to identify objects, process information, we can see that we're still pretty far away from developing human-like sensory perception capabilities. So for example, systems that are trained through deep learning still have very poor color consistency. One real-life example of this just being self-driving cars, which use computer vision to power themselves. But if you have a self-driving car driving down the road and it sees, let's say, a black piece of tape or stickers that are on top of a red stop sign, it would be easily fooled by that, right? It would get confused as to if that's even a stop sign. But for humans, if we saw that red stop sign, it would still be fairly easy for us to know that that is a stop sign and that we need to stop when we reach that. And so currently, a lot of these algorithms that exist for computer vision are not able to do this. And they're also very much largely limited and incapable of extracting depth from three-dimensional information when given, static images that they're often trained on. So the actual translation from, static images to 3D information in real life is missing. And similarly, going from simulation to real life is also really difficult. And so although we can get some promising results in simulation, getting those results in real life is a lot more difficult. The other area that there's a lot of work, but we need, still a lot more focus on is just natural language processing, or NLP. So if we think about humans, we're able to record and transmit our skills and knowledge through a variety of mediums, whether that be books, articles, blog posts, videos. But in order for an AI system to fully understand a language, the complexities between them, it needs to be able to consume all of these sources of information with a full comprehension of what those sources actually mean, but also the context at which they're being said or being held at, to be able to hold conversations or produce text in a way that feels very natural to the way that humans would communicate with each other. And so today robots are not able to do that just because of the complexities that exist within the millions and billions of languages that exist out there, and a lot of the conventions that also exist within them. So the last area that really needs some development is within manipulation. And so this is where a lot of research alongside NLP, I think currently is being done. If you think about humans, it would be really easy for us to, let's say, just retrieve a set of keys from our pocket. But very few of us would let any sort of robot manipulator, or I don't know, a humanoid hand actually do that task for us. Because in fact, that task would be very, very difficult for a robot to do, because it would require just a high amount of precision and calibration. So there's a lot of research being done in this space. Companies like OpenAI that showcase demonstrations where they trained an RL algorithm to teach a robot hand to solve a Rubik's Cube problem, being one example of how some of that work is being developed. And so you can see, Rubik's Cube problem, that's already a very complex problem and task for even just humans to solve, but for a robot to do that, it's even more difficult. So outside of my work, there's obviously a lot of global companies that are working on these problems, companies like Google Brain, which have a huge focus on deep learning and figuring out ways to develop algorithms and approaches where we can run these without the algorithms being as data extensive, or being able to develop lighter weight architectures that are able to compute at a much faster rate while still getting good results with these models. So they're very much more research heavy and trying to really push the industry forward. There's also companies like OpenAI that are working on making sure that AI itself is just safe and ethical, right? If you think about a lot of the implications that come from AI, although there's a lot of good, there's also a lot of areas where we still need to develop like equality and being able to develop more ethics within these models. And then we have Facebook Research, which is doing a lot of work within social media, so understanding fake versus real content, and helping to overall just make the social media process a lot better. Then we have companies like Google DeepMind, which are working on building a lot of the Google products that we interact with and use just on a day-to-day basis. Another company that I wanted to highlight that you might have heard of or seen in the news is Neuralink. And Neuralink is working on developing a chip that is connected to wires, which are able to fan out into the human brain, and capable of both recording the brain activity as well as simulating brain activity in just a matter of seconds. And alongside this, they've developed the Neuralink robot, which is used to implant the chip and do surgery when they're actually implanting this chip. Just because this robot actually has greater precision and actually reduces the risk of damage to brain tissues rather than having a human do it. And the main reason is because humans are just prone to making errors, and so a lot of their work is being done as well to increase the precision of the robot that they have. This is a quick demo of something that they showcased where they integrated this chip into a pig. And so they were able to capture the brain activity that was happening as this pig was moving around and doing different tasks. And as you can see, they've showcased what the actual brain activity of the pig was versus what was being captured by the chip here. And they're using also a lot of different ML algorithms in the back end to process these signals and eventually draw insights from them. They also recently showcased a monkey with chips that were embedded on each side of its brain, and it was playing Mind Pong. And so although he was trained to move this joystick, during the actual demo, it was unplugged. And so he was controlling the paddle simply by just thinking about, moving his hand up or down. And so they did this by recording and decoding electrical signals from the brain using over 2,000 electrodes that were implanted in the region of the monkey's motor cortex. And that was also coordinated by the hand and arm movements that it was doing. And so using this data, they calibrated the decoder by mathematically modeling the relationship between patterns of the neural activity and the different joystick movements that they were able to produce. And so although this work, currently it's very early stage and really at the stage of just testing and understanding if this is even feasible, but I think the greater implications of this are huge for being able to potentially cure mental illness, such as anxiety or depression disorders, or cure conditions like Alzheimer's, dementia, and spinal cord injuries. So within NLP, OpenAI is obviously a huge player. They're working on a lot of applications, one of their recent frameworks being GPT-3, which uses deep learning to produce human-like text. And so it's a powerful model that uses NLP, which is used to almost just generate and create text that is coherent and also useful and understandable by humans. And so in the future, you can almost imagine, using applications like this to become a writer and being able to actually just write content like books, or using AI for marketing, writing recipes, and also just in general, training machines or humanoids for being able to converse with humans. So when I think about the future now, I think about a world where people like Sarah no longer have to buy really expensive and difficult to use prosthetics to live her daily life. I imagine stroke patients being able to easily get access to cheap and effective rehabilitation equipment that will allow them to recover their motor functions. I imagine telerobots being used during surgery. And what's really exciting to me is that we're really just touching the tip of what is possible with AI and this future that we're working towards with AGI. And I'm really excited when I think about what this future will actually look like and how that future might fit into my life. And so that's really what I want to leave you with. And that's what I want you to be thinking about is, how will this future of machine intelligence converge over the next couple of 5 to 10 years? And how do you think that future, is going to fit into your life?